Think about it for a second. It's completely invisible, but it powers literally everything in your life. Your phone, your lights, the entire modern world, it all runs on electricity. We totally take it for granted, but this invisible force was once at the center of a huge technological war, a battle that decided exactly how our world would be powered.
Yeah, that's right. Every single time you plug something into an outlet, you are tapping into the winning side of a massive fight that went down over a century ago, a rivalry that determined the future of power.
And it all kind of kicked off right here. This is Thomas Edison's Pearl Street Station, which in 1882 started lighting up a tiny little part of New York City. The idea itself was mind-blowing. One power plant serving a whole neighborhood. But his system had one massive critical flaw.
And that flaw led directly to what we now call the War of the Currents. Now, this wasn't some friendly debate in a lab. Oh no, this was a high-stakes, all-out war between industrial titans, and the winner would get to build the future.
So, here are the two contenders. In one corner, you had Thomas Edison, and he was all in on direct current, or DC. Just think of it like water flowing in one direction down a hose. It's simple, but it runs out of steam pretty quick. It just couldn't travel very far. In the other corner, you had Nikola Tesla and George Westinghouse, and they were backing alternating current, or AC. Now, AC was the real game changer, because its voltage could be easily cranked up or down with a transformer. That meant it could be sent hundreds of miles with almost no power loss. That was everything.
So, spoiler alert, AC won the war. But to really get why it won, and to understand how this stuff actually works inside your walls today, you kind of need to learn the language. So let's decode some of the basics that make it all happen.
The first and most important rule is the circuit. For electricity to do anything at all, like turn on a light, it has to have a complete, unbroken loop. It's got to go from the power source through whatever you're powering and all the way back to the source. If you break that loop anywhere, everything just stops. That's a non-negotiable rule.
And this is a perfect, super simple picture of what that looks like. The battery is the source, the starting line. The current flows out, it goes through the light bulb, which we call the load, and does its work, creating light. Then it travels right back to the battery, completing the circuit. Easy, right?
Okay, now let's talk about the three key players here. The best way to get it is to think about water in a pipe. Voltage is like the water pressure. It's the push. Amperage, or amps, that's the flow rate, how much water is actually moving through the pipe. And resistance, well, that's anything that makes the pipe narrower, trying to slow that flow down. Every single electrical thing you own is a balance of these three forces.
And this is where we have to have a healthy respect for electricity. Get this, you can build up 400 volts of static just by shuffling your feet on the carpet, but that little zap is harmless because the amperage, the flow, is tiny. Your wall outlet is only 120 volts, but behind it is the entire grid, which can pump out an almost unlimited amount of amps, and that is what makes it so incredibly powerful and dangerous. So if it's so powerful, how in the world does AC electricity travel from a huge power plant, maybe hundreds of miles away, and arrive safely at your phone charger? Let's follow that amazing journey.
I'm sure you've seen these things before. They look like these crazy metal jungles, and you can almost hear them humming when you drive by. They're called substations, and they're basically the air traffic controllers for the power grid, directing the flow and managing the voltage of all that electricity.
The whole trip is really a story of changing the voltage up and down. It starts at the power plant, where they immediately step it up to super high voltage so it can zip across the country on transmission lines efficiently. Then, at a regional substation, they step it down to a more manageable level. And finally, there's usually a transformer on a pole or a green box in your yard that steps it down one last time to the 120 volts you use. And this whole incredible system, it only works because of AC's ability to change its voltage.
All right, so this immense power has arrived at your doorstep. Now, what stops it from going wild and burning your house down? Turns out, your home has a few silent, secret bodyguards built right into the walls.
Your first line of defense is grounding. Ever wonder what that third round prong is for on a plug? That's it. It connects to a special wire that provides an emergency exit for any electricity that might leak out of an appliance. Instead of going through you, it takes a safe path right down into the earth. It's an escape route for rogue electricity.
Come on, we've all done it. You plug in the coffee maker, the toaster, and the microwave all at once, and suddenly, darkness. Well, when you try to pull too much power through a wire, it gets hot. like really hot, and that's a huge fire hazard. So what's our protection? If you're in an older house, you might have these things. Fuses. A little strip of metal inside literally melts and sacrifices itself to break the circuit and stop the overload. The modern version, which most of us have now, is the circuit breaker. It's just a switch that senses the overload and trips itself off. The best part? You just go and flip it back on. No fuss, no muss.
And then you've got the super protector, the GFCI. Think of this as the secret service agent of outlets. It's constantly measuring the electricity going out and coming back. The instant it senses the tiniest little imbalance, which could mean the current is leaking through you, it shuts off the power in 1/40th of a second. It's so fast you might not even feel it. That's why you always find them near sinks in kitchens and bathrooms.
So, from the war of the currents to these safety gadgets in our walls, the whole story has been about big, centralized power being sent to us. But what if that's all starting to flip on its head? Because we're definitely entering a brand new era.
For pretty much the last century, this chart is what our power has looked like. You see a ton of coal, a ton of natural gas, all coming from those massive, faraway power plants we've been talking about. But there's a new technology that's starting to shake this whole model up.
And that revolution is photovoltaics, or as we all know it, solar power. What's so wild about solar is that there are no turbines, no steam, no moving parts. It just takes sunlight and converts it directly into electricity. It's almost like magic.
And believe it or not, this idea has been around forever. The basic effect was discovered way back in 1839. But it was just a lab curiosity until 1954, when Bell Labs made a solar cell that actually worked, mostly for satellites. But the moment it really started to matter for you and me was in 1978, when a law was passed that said power companies had to buy back extra power from small producers.
And that brings us to net metering. It basically means your house can become a tiny power plant. When your solar panels make more power than you're using, your electric meter literally spins backward and you sell that power back to the grid. But here's the best part, the full circle moment. Guess what kind of electricity solar panels make? DC, direct current, Edison's old system. So in a weird way, we're going back to Edison's idea of local power generation, but we're doing it on Tesla's winning AC grid. It's like the best of both worlds.
So just think about that shift. For 100 years, we were just consumers. We paid the bill. Now more and more, we're becoming producers too. The grid isn't a one-way street anymore. It's becoming this smart two-way network. So the big question isn't just where our power comes from anymore, it's what role will you play in making it?